Welcome to Master of Science with host Professor James McCanney. The good professor's career spans 50 years as a university teacher, scientist, and engineer. Each week, he will explore the rapidly changing world of science as many long-held theories are crumbling under the weight of new data. He will cover the fields of geology, archaeology, meteorology, oceanography, space science, astronomy, cosmology, biological evolution, virology, energy, mathematics, and more. So please welcome the host of Master of Science, James McCanney.
Good evening again, and welcome. We're going to have a lot of fun tonight. One of my very favorite topics, we're going to talk about Jupiter's red spot. And this brings a whole plethora of other concepts into play: magnetic fields, fusion. Well, you'll find out. It's much more complicated than meets the eye. It looks like just this cyclonic storm. When Galileo first looked at it, they thought it was just like some spot on the planet. They didn't really realize, and it was only until we got close-range observations with satellites that they really understood that this was not some kind of surface feature on Jupiter, but it was actually an active atmospheric condition. Also, I hope to get later in the show talking about lighter-than-air airplanes. This is something that's coming along, and I think you're going to see this. You may, sometime in your lifetime, ride in an airplane that's lighter than air. And I'm not talking about the big dirigibles. I'm talking about they're small, personalized aircraft. And this is what's very interesting, that you could buy for a relatively low price in an aircraft and land it and take off any place you want. One of the big costs involved in owning an airplane is the airport fees and finding an airport to land, and then when you get to wherever you want, you have to then have other transportation, of course. But what if you want to go out in the middle of nowhere and land? Well, you just can't do it with a regular airplane. You need a very specialized landing strip to land and take off. But what if you could go camping, let's say, or what if you went on a geological survey of some area and you wanted to land out in the middle of nowhere, or just go camping, you know, on the shore someplace? Or anyway, we'll hopefully be getting into that. But back to the topic of Jupiter's great red spot. Now, there's just so many topics to cover here. Let's start with Earth, because Earth has some properties that are very similar to those of Jupiter. In fact, I've talked about this before, where the Earth has bands of basically bands of wind bands, you might call them, that circumvent the Earth. And there's one at the equator, which is an electron belt, which moves westerly. There in the middle latitudes, there are two belts that move easterly, and those are positive ion belts. Those drive the lower level winds and jet streams, they're called. And then up at the poles, the North and the South Pole, you have what are known as the ring currents. And they are rings, literally rings, that wrap around the Earth in the polar regions. But they move in the same direction as the equatorial belts. They're mainly electrons. But those situations can change, and they are coupled to Earth's magnetic field. So we're going to be talking about Jupiter's magnetic field, which is a little bit different than Earth's. But let's take a look at Earth's magnetic field. Now, when you get a compass in your hand and you walk around and it has the needle north, it assumes, or you assume, that the magnetic field is perfectly aligned with the spin axis of the Earth, and that's not true. The spin axis of Earth is at what we call the North Pole. It's where Santa Claus lives. And that's the spin axis of Earth. So when you spin the Earth, you look at the Well, let me just grab my globe here. Let's talk about the poles here, the North and the South Pole, and that's where you have the pins in the globe. So that's the North and the South Pole. Those are the geographic North and South Pole. But the magnetic North Pole is way down here in Canada, in the Northwest Territories of Canada. And it's slowly moving up to this North Pole. And there's a reason for that, because Earth had a pole shift within the last 10,000 years. That's when some large object came by Earth, and with a gravitational wave, I've talked about this on the show. Go back and listen to those previous shows if you've missed them. But an object came by and actually torqued the mantle and the crust of the Earth over its viscous molten inner part, core, and it turns out that the magnetic field is associated with the permanent magnetic field, and that's shifted also, and it's slowly working its way back up to true north, the North Pole. Okay, and so let's talk about that permanent magnetic field, because there's many different layers of the magnetic field of Earth, but we have a fairly strong magnetic field, and that's due to iron in the surface of the Earth. Now, how does iron become a magnet? Well, every little iron atom has unpaired electrons, and this is basic physics. And what happens is the spin of those electrons can align, and when they align, they form a magnetic field. And then, but when an iron liquid is in a liquid form and it's trying to solidify, if you put that piece of iron that is liquid into a magnetic field, an external magnetic field, and let it cool through what is known as the Curie temperature, then those iron atoms align and those magnetic fields align, giving you a permanent magnet. So then when you take the external magnetic field away, the little piece of iron retains its magnetic field. That's a permanent magnet. And there are other types of modern materials that they use in, say, wind generators or in other types of magnetic devices. But cobalt, iron, nickel all have the properties of these unmatched spin in electrons in their orbits, and give them the ability to become magnetized. So that's a permanent magnet. Now, the question is that this is something that geologists won't even ask, let alone answer, is if Earth has a permanent magnetic field, then it had to have had that iron, nickel in the crust, in the core, etc., would have had to have had a spatial magnetic field around it for literally millions of years in that northerly direction. But where did Earth get this external magnetic field? That is the million-dollar question. Well, it turns out that in the formation of the planets, there are electric fields and electric currents and magnetic fields. So this gets into a rather complicated topic, but I don't want to dwell too much on Earth. I want to jump out to Jupiter. So here we go. Here's the first view of Jupiter. This is the entire planet with a red spot. You can see that prominently viewing in front. And I have some arrows here. There are the blue arrows. Now, first of all, the red spot is a cyclonic storm, and we'll talk about that. It's an interesting cyclonic storm, but then also you see the blue arrows, which point to other cyclonic storms. So there's a lot of cyclonic storms here. And the great red spot can chew up, it can actually assimilate other spots, and apparently over the hundreds of years that it's been observed, it's actually gotten smaller. So is it going to go away? That's what some people think. And the question is it like a hurricane on Earth in the fact is that, yes, it is. It's a lot like a hurricane. We'll be talking about that. But look at the orange arrows. They indicate bands. Now, if you just had a planet that had a heat source in the middle, and that was it, and floating around in outer space, you would not have this kind of band situation. You would have heat relatively evenly distributed through the atmosphere, and you wouldn't have this band situation. So in a minute I'll show you a video with the bands, the counter-rotating bands. And this turns out to be very similar to Earth, in that Earth has these counter-rotating bands that are caused by electrical currents, and they're part of the magnetic field. And so Jupiter has the very same thing. Earth has 5 bands: the equatorial band, the 2 temperate climate bands going easterly, and then the 2 polar bands. Jupiter has 13, and in a planet like this, well, Jupiter's not really a planet, it's a small star, but you always have an odd number. That odd number, one of them is the equatorial one, is in the westerly direction. It's the way it just turns out. And then you have alternating east, west, and the Great Red Spot just happens to sit between 2 of those bands. So one might think that that's what's powering this cyclonic storm. It's really not the case. The storm itself goes deep down into the atmosphere, and I have a concept that I've been working on in the background, and my guess is that something hit Jupiter, an object, and it buried in, and it stuck in the core someplace, and it's actually a lump, so to speak, at the base of the Great Red Spot, and that is one of the issues that is causing it to form this hurricane-like storm. Now let me quick jump back to Earth for a minute and talk about hurricanes. Now, the reason a hurricane, I talked before about hurricanes and how they formed. They form because of the vertical electric field of Earth, and that is an electrical situation that goes back. It's powered by the sun, by the sun's electrical fields that are generated, very simply put, because there's an excess current of protons in the solar wind. And this is a common feature of fusion-based objects. That's one of my discoveries. And so, at any rate, the hurricanes form because ions are moving upwards in that vertical electric field. They spin. The Coriolis force causes them, as the current goes up, it causes that, the Coriolis force causes it to spin, and that's what causes the eye of the hurricane and the hurricane itself. And so Jupiter is very much the same. It has a vertical electric field. And so all of this activity, in fact, I hope we get to Saturn here, because that has a lot of very similar activity. And so these are cyclonic storms. They're driven by electric fields, vertical electric fields, that is, vertical in the atmosphere. And so I have a hunch, it's just a hunch, that something big came in, landed in Jupiter, and that is at the base of the Great Red Spot. But back to Earth hurricanes, what stops a hurricane when it makes landfall? And the actual result is that it electrically shorts out to land. And you can see this is the case. The other thing about hurricanes is the leading edge, when they're coming into land, have a lot of tornadoes. That's one of the characteristics. And so the Great Red Spot has a very similar situation where you have a lot of tornadoes, in other words, smaller cyclonic storms on the leading edge. So it's very similar to a hurricane, although it's in a sense reversed. It has a high pressure cell instead of a low pressure cell. And so instead of being an eye of a hurricane, the eye of the Great Red Spot is filled in primarily with sulfur dioxide and sulfur-based compounds. And that's where the reddish tint comes from. There's a lot of sulfur out by Jupiter. And so anyway, look at the arrows once again here. The arrows, the orange orange arrows indicating the direction of the co-rotating bands, and the blue arrows indicating locations of other cyclonic storms on Jupiter. So anyway, here's a close-up look at the Great Red Spot. And also, there's more arrows here looking at the various other cyclonic storms. Now, this photo is the most interesting of all. There, on the left, you see Jupiter and the Great Red Spot in the infrared. What does that mean? This is heat. This is in where it's very bright. There's a lot of heat. So Jupiter is not just an object with a hot core. No. It is an object with a lot of activity in its atmosphere, and this is fusion. And this is one of the quandaries that I had to deal with when I was looking at Voyager and Pioneer data from Jupiter. This was originally coming in, this is back in like 1979, that it had the same properties as the sun. It has the exact same atmospheric composition of hydrogen, helium, etc. So it was clearly not a planet, it's a star, it's a sunlit star, but it has fusion. It has a proton wind coming off the surface that was actually measured by the Voyager spacecraft and actually published in one of the Science articles. Brad Smith was the author, lead scientist, and he published that there is a proton wind coming up off the surface of Jupiter. So Jupiter is a small star with ongoing fusion in its atmosphere, but the core is much too small to produce gravity-based fusion. And that was the quandary, and that's when I realized, well, the sun is the same. The sun's fusion is in its atmosphere. And so the end result is that there is fusion going on. Well, what's causing the fusion? It takes energy to kick it off. And the answer is that it is caused, the fusion reactions are kicked off by energetic lightning bolts in the atmosphere. So that leftmost picture, and we're going to see a close-up of that. The middle picture is in the visible. That's what you'd see with the naked eye. And the rightmost picture is in the ultraviolet. So, okay, back again. And I want to preface this by saying that if you asked a NASA scientist what causes the magnetic field on Jupiter, if they were honest with you, they would say they don't know. And if they were dishonest, they would go through some kind of whitewash explanation that really isn't an explanation at all. In fact, when you see some of their explanations of what's going on, like the electrical current between Jupiter's poles and the moon Io, they have it backwards. They are believing that the magnetic field causes the current when it's really the reverse, because you cannot create a magnetic field. These magnetic fields don't just exist, and that's one of the things that I learned about being around standard scientists, is they'll talk about magnetic fields all day, or magnetic field reconnection, or all of these other ideas about magnetic fields, about magnetic fields creating currents, but they can't tell you where the magnetic fields come from. And in the free plasma environment of outer space, magnetic fields just don't exist. They just don't come out of nowhere, and there they are, like magic. Okay, so anyway, look again. I want you to look at the red spot, this big spot in the lower part of the planet there. In the left, the middle, and the right-hand photo there, the images, and you'll see that the red spot is darker. And so what that means is it's cooler. It's a very cool area. But if you look at the left, you'll see the fusion going on between the bands, and that's where the lightning is. Between those co-rotating bands, because why? Because they're electrically charged. You have positive current going in one direction, you have negative current going in the other direction, and so you have massive lightning between those bands, and that's where the fusion is. But you'll see that it goes around the Great Red Spot, especially on the left there. You see it in the infrared. You see the fusion actually going around the red spot. So the red spot is very cool. And if you look at the right-hand photo there, it is the infrared. So it's very bright in the infrared. It's like a neon light bulb. It's a little star, except you really, it's not lit up in the visible spectrum like, say, the sun is. But there's a lot of energy coming off of Jupiter, and it's been measured to have many times the amount of energy leaving as comes from the sun. In other words, the sunlight is not producing the heat at Jupiter. There's something else going on there, and it is called fusion. And so that tells us also something about laboratory fusion. They have these big accelerators and things like that. They always talk about creating fusion with magnetic bottles. It's the total wrong approach. It's the total wrong approach. And so the whole concept of fusion or cold fusion, which is low temperature fusion, is right there, right in front of you. It is simple, and of course you have to have scientists who would understand this and then capitalize on that. Okay, now here's a close-up of that infrared photo of Jupiter. Now you look at some of the spots. You can see them up towards the top or down towards the bottom, and you see, where do those spots exist? Those bright spots. They're in the groove between the co-rotating charged bands. A lot of lightning and a lot of electrical currents, and it's that vertical current that causes the cyclonic storm, the Coriolis force. And you don't see them too much around the equator because the Coriolis force there is very minimal. It's more up in the mid-latitudes. So you can see dozens and dozens of small spots, very bright meaning that's where the fusion is, and then and you do see these bands that are extremely bright. In fact, there's another, let me go to the next photo here. This has orange boxes around these extremely hot areas. And so that is a place where you have a good deal of fusion going on. Okay, so let's go to the next one. Here's the picture in visible light, and that's what we see with the naked eye. Here are some other indicators of areas, hot spots in storms, other storm systems on Jupiter. And here's the infrared. Now, imagine this was a neon light bulb. You know, what's interesting also is they always show you the side of Jupiter with the sun that's lit up by the sun. And so they never really show you the side of Jupiter that's dark. And these are from the Hubble, which is a shot from Earth. So in an Earth view, or pretty much any Earth view, you're going to see only the bright side, the sunward side of Jupiter. But when I was working with Russian scientists in the mid-1990s, they did a lot of work relative to the dark side of Jupiter. In fact, when there was a series of comets, they were called Schumacher-Levy 9, there were 21 pieces of comets that came in, they were actually able to see X-rays bouncing off the moons of Jupiter, which were on the far side of Jupiter at the time. And so they were able to actually see, almost like a mirror, the energy coming off the explosions that happened when those small comet pieces, and these are not ice balls, these are very high energy discharge comets that came into the surface of Jupiter. And that was in kind of I think it was about 1996, 97 in that time frame. Okay, so now what I want to show you are the rotating bands. So a little video piece here. And what you see are the co-rotating bands. Like I said, if you had a planet with a heat source, and that's all you had for the heat source, then you would not have co-rotating bands, not by any stretch of the imagination. So the only way you're going to get co-rotating bands is if you have these fusion engines going on, which are creating electrical currents, and then this is coupled to the greater magnetic field. So Jupiter's core may have a magnetic field, which would be interesting because a hydrogen atom has a single electron, and therefore in the correct state could be the source of a significant magnetic field because it's a single electron is not paired. It's not paired, and so the spin of the electron would not have a pair, and therefore solid hydrogen would have a very good propensity to create a magnetic field, a permanent magnetic field in the core. Okay, so moving outwards, however, just like Earth, now let's go back to Earth and talk about Earth's magnetic field. First of all, you have the core magnetic field, which is a permanent magnet. Above that, you have the, let me get my little globe here again. Okay, so you have in the Earth itself, you have a permanent magnetic field that is locked into the iron, nickel, other minerals, primarily iron, in the Earth's surface. Then in the atmosphere and up towards the ionosphere, you have these ionic jet streams that circle the Earth, and those are electrical. In the temperate zones, you have them moving in the easterly direction. In the equatorial region, you have a westerly moving electron belt, and then around the poles, you have westerly moving electron belts. Those are the pole currents. Okay, so the same situation happens with Jupiter. Now, what happens above there, you have what are known as the Van Allen belts. The Van Allen belts are radiation belts, which are it's positive protons primarily and some electrons that are co-rotating in bands around Earth, and they're really orbiting in Earth's magnetic field. And they couple with the rest of Earth's magnetic field to give it another layer of magnetic field. And then out about 30,000 miles between Earth and the Sun, the Earth's magnetic field fades away and is actually coupled with the electrical currents coming from the Sun and the solar wind. I've talked about this before, where the solar wind comes out, it sees that magnetic field, the electrons go one way, the protons go the other way, which creates another layer of magnetic field, because you have those and that also feeds the electrons and protons that are in the Van Allen belts. So Jupiter is doing the same thing. However, it has another complication in that Earth does not have ongoing fusion in its atmosphere. Jupiter does. So what does that do? That creates a proton wind. This causes Io, the innermost moon, to have a ring of material that's following it in its orbit, ionized, basically sulfur dioxide primarily. And of course, then again, NASA has this completely backwards. They say that the sulfur dioxide is coming off of Io. And supposedly, doing this for 4.5 billion years, there wouldn't be, poor little Io wouldn't be there anymore. Which brings up actually a very interesting point. That, remember the dirty snowball comet model? That's been around since Kepler, Middle Ages, but anyway, revived by Fred Whipple in 1950 when they had to come up with some kind of theory for how comets worked. And then revised, in that day and age, it was called the ice ball comet model, and it got revised into the snowball comet model, then the dirty snowball comet model, and then the really dirty snowball comet model, because there ain't no snow or ice or water on the nucleus of the comet. But the point is that the moons of Jupiter have a lot of ice on them, and they're out there in the solar wind. They're not protected by Jupiter's radiation belt. The three big outer moons, Galilean moons, have a lot of ice on them. And if this dirty snowball comet model were correct, then they should be the biggest comets you ever saw, with the ice sublimating off and going off into outer space and forming these huge tails. And of course they don't, which is just one of the thousands of contradictions you run into when you try and look at, peel back the first onion layer on that dirty snowball comet model. Another one is that it's self-defeating. As it becomes bigger and bigger, the coma itself would block the solar wind and solar radiation that's supposedly going to melt it. So how does that work? Anyway, no, I could go on and on about that foolishness. But back to Jupiter. So look at all of the factors that Jupiter has in producing its magnetic field. And the reason I'm talking about magnetic fields is because these co-rotating rings on Jupiter, these bands, co-rotating bands, are ions, electrons, etc. And they're moving in opposite directions. And like I said before, this would not happen if you just had simply a heat source in the middle of the planet, which was somehow creating the weather. Okay, so now we're going to take a look at some weather patterns. And first, we're going to start looking at Earth here. Look at these patterns, and then we're going to go back to Saturn, Saturn's south pole, where there is a hexagonal pattern. And these are wind patterns that are deep down in the atmosphere, which we really can't see. But you can see them on Earth. So first of all, take a look at this picture of Earth here. This is looking at the South Pole. And that's very interesting also, as this appears to occur at the South Pole. And look at the, well, it's not really hexagonal, but I have photographs. I couldn't find them for this particular show, but I have photographs of this part of Earth, these wind patterns that are a perfect hexagon. And so what happens is you have a central storm that's a cyclonic storm driven by vertical electric field, just like hurricanes. That's what it is. It's a hurricane. And then you have 6 other storms of pretty much the same size stationed around it, and that gives you the hexagon. So the wind patterns, but here's a great example of nearly a hexagon. It's a little bit off. And then if you look at the northern hemisphere, the next shot here, you will see that you don't have that hexagonal pattern, but you do have lots of storms, cyclonic storms. And of course, here's another one of these silly science, that hurricanes form from warm water. And here you see a number of hurricanes right off of the way north. This is looking directly from the North Pole. And by the way, the biggest hurricane in history was called the Perfect Storm. They made a movie out of it. And it was a combination of 3 overland hurricanes. In my weather book, I call them himicanes because they're overland. Just a little play on words there. But the one came across, in fact, I was in this. It was October 31st. It's called the Halloween Blizzard of 1991. It happened up in the border states, the states next to the Canadian border. But this storm came across, and it dumped 3 feet of snow one day. Then the eye went through. It was literally a hurricane. And that day was a beautiful sunny day. And they tried to get the plows out, but the plows couldn't even handle, there was so much snow. The next day, it snowed another 3 feet. So you have 6 feet of snow in a couple-day period. It took them about 2 weeks to really plow out from under that. That was a horrific amount. That was just one of the 3 storms that combined to make the perfect storm. The second one came across the southern U.S. and came up across the Appalachian Mountains, and it killed a lot of people. A lot of people died because of the cold and being just stranded in their cars, etc., through Appalachia, and that came out up the eastern seaboard. Then the third one was a true hurricane, came up the Atlantic seaboard. Those 3 storms combined to make what was called the perfect storm. So now we're in early November 1991, and you have the biggest hurricane in history forming in the North Atlantic with frigid cold water. So where's the warm water, folks, that makes this perfect storm the biggest storm in history? So in this picture, though, you can see many cyclonic storms, basically what we would typically call hurricanes or cyclones, on the northern hemisphere, way up in the Arctic region. Okay, so now we're going to look at Saturn's south pole. It's a hexagonal wind pattern, and these are different images of different depths down into the atmosphere. And we're just going to go through some other photographs here of Saturn's atmosphere. It looks just like Jupiter's, and they're very much the same. They're very much the same. Here's a photograph of Saturn showing its just electrical nature. I mean, it's very electrical. Saturn is more active electrically than Jupiter, and I talk about that in my books and my scientific papers on the nature of the planets, etc. So Saturn also has fusion in its atmosphere, and it and Jupiter are discharging the solar capacitor, as is Earth, as is every body in the solar system, discharging the solar capacitor, acting like a comet. And so the last thing I want to show here is Neptune. Now, Neptune has a storm, a cyclonic storm that's been going and going like the ever-ready bunny. As long as people have been able to observe Neptune, it's been rolling around the planet. And so you can see it's also lit up. It's bright, and the same issue. This is electrically driven storm in the atmosphere of Neptune. So all of these are electrically driven. That's the point. The magnetic fields, as I said before, magnetic fields simply don't exist in outer space. I still get these emails from meetings, conferences to go to, trying to convince people that magnetic fields convey electric currents. It's the other way around. If you look at Maxwell's equations, a magnetic field can induce a current in a wire if there's a change in the magnetic field, like a moving magnetic field, like a magnet coming and then leaving, but in a wire that is contained. You cannot create an electric current in free space with a moving magnetic field. It's the other way around. In free space, and a lot of people get this confused because they think, oh, it's like a motor. Well, no, a motor has wires, and those electrons are contained in the wire, and they can't leave the wire, and that's what creates the force, and that's what, as the current is generated in the wire when there's a changing magnetic field. But it's not the case when you have a plasma environment in outer space. It does not work that way. So these are things that physicists at a high level should understand. And unfortunately, with most astronomers, they have very poor physics backgrounds, so they don't understand these things, and they come off with these wild claims about magnetic fields here and there and magnetic field rate connection, all kinds of things that simply are not true. Okay, so I hope that covers the dynamics of Jupiter's red spot, because it's just one of many, many storms in the big planets. Why am I calling them planets? That's a habit that goes back to childhood. Jupiter and Saturn are small unlit stars. Unlit meaning not lit in the visible spectrum. So I hope that makes sense. Once again, check out my books, the weather book, all of these other books that I've talked about on this show. Go to the webpage jmccsci.com, and it's quite an educational process to go through and understand the physics of how the planets work. But it all makes sense once you understand it's driven electrically, and that electric power, there's three main sources in the solar system: Jupiter atmosphere, Saturn's atmosphere, and those are local, and then the sun. And the sun puts out far more energy in the form of electrical energy than it does in the form of visible energy. Okay, switching gears now, we're going to talk about lighter than air aircraft. And this is a very interesting topic because these are coming back in kind of a different way. They're more personalized. And there are efforts underway, private companies and some government-funded projects through aerospace corporations to build the big blimps again, what they call the blimps. Like if you've seen a sporting event, then you've seen the Goodyear blimp, just floating above a stadium or whatever. or an outdoor event like I was just watching the Tour de France on television, and they have I don't know if it's the Goodyear blimp, but a blimp up there, high up, to give aerial shots of the sporting event. Okay, so there's all of this going on, of course, hot air balloons, and a long time ago, in the 1800s, there were groups of people who, and individuals, a lot of individuals who had great ideas. They understood the principle of making a lighter than air aircraft, the idea that hot air rises, and that if you contain that hot air, you can get lift out of it and then put some propellers on it. Or there's one, I'll show you a picture of here, actually had like little fish fins type of arrangement where they would move it and get propulsion from that. But what's going on is that the personalized vehicles are coming back. There are people that are working on like drone type, where you have the 4 propellers to lift it, and people are building those because the technology is pretty well established, and they're very reliable. And that's another thing that's going on. But the use of something like helium in a small personalized craft is what I'm talking about, and that's what we'll get to at the very end of this. And so I'm going to go through some of this history. Some of you may have seen parts of this, but I think it's very interesting because, for example, say you're doing a project and you want to go out in the middle of nowhere, then there's a lot of places they're just not accessible even by foot or by motorbike or other means. It's just the just rugged terrain, for example. And to get out into the middle of a field, I can think of places. For example, I have a video, not a video, I'm sorry, it's a CD on my webpage. It's called 110 Photographs, High Altitude Aerial Photographs of the American Southwest. And go check that out. It's really interesting. It was, what year was that? I can't even remember. It was decades ago. I was in Los Angeles, and a friend of mine had a aircraft that could reach high altitudes, like 45,000 feet high altitudes. And so the idea was, at the time, there was a big dust storm coming in from China. And the interesting thing was that when you got up to high altitudes, you could see that layer. You could actually get up above the layer of this dust. It was blowing in from the Gobi Desert from China, And so anyway, the day that we took off, it was so absolutely clear. It was unbelievable. It was one of those things where maybe once every 10 years it might be that clear over the entire American Southwest. And so we get up over the Mojave Desert, and I have my camera equipment with me, high resolution, at that time, digital camera. And so I started taking pictures, of course, and that was the idea. And it was up high enough that you could actually see above the blue of the atmosphere and see above into blackness of outer space, literally. And so anyway, I looked down, and I was able to get the camera up to the window of the aircraft, and so we decided to start flying east towards Denver. And so anyway, I ended up flying all the way to Denver. And this series of photographs covers the entire American Southwest. It's really worth seeing. And of course, it was as the sun was coming up, so you get a lot of detail because of the shadows of the early morning. So you could see a lot of detail in the American Southwest. But anyway, there are vast regions of the American Southwest that are just inaccessible. And it would be fun to go out there and explore some of these places, like I say, that you just could not get to. And with a vehicle like this, literally, you could take off, you could go at low speeds, you could go at high speeds, you could go up to probably 150 miles an hour if you wanted to, but very inexpensive to operate. because the vast majority of energy spent in flying is in opposing that weight, the weight of the aircraft. So anyway, let's get started here. We'll start going through some slides. This first one just is somewhat of a collage of aircraft, different kinds of aircraft that currently operating, everything from the Pegasus blimp, and which is a modern version of the old Zeppelin blimps, and made in pre-World War II Germany. And those are very interesting. We'll be talking a little bit about those. So a hot air balloon, one of the original ways to travel with lighter than air. And then a personalized flying craft, all kinds of gliders, etc. Every shape and form of possible aircraft has been built and tested. Okay, here's a guy on a what do you call it, a glider, hang glider, and yeah, you have to be pretty, it's not my cup of tea, believe me, but it's very interesting, and I like watching the movies, or these guys that put on a suit and fly like a flying squirrel. That is, okay, that's interesting. So here's the FAA classifications according to categories of aircraft. So you have airplanes, single engine for land, multi-engine for land, single engine for sea, multi-engine for sea. Rotorcraft like helicopters, hydroplanes, what do you call it, hydroplanes or tilt rotors. And then the lighter than air, or aerostats. And airship, blimp, dirigible, or balloon, hot air balloon. And then there's the glider category, like a sailplane. But anyway, there's kind of almost a new category, like I say, for individual aircraft that are assisted. And now there's something about if you have aircraft that's completely suspended in the air by helium, then it becomes difficult to control. So you don't want 100% of your lift coming from the helium or hydrogen. Hydrogen is another much less expensive form, and it actually, hydrogen has a much better lift capability, about 20% more than helium, but it has certain risks also. But in this modern age of hydrogen, you can also use the hydrogen as a fuel for either fuel cells, for electric engines, etc. Okay, so on to the next. Here's an example of a drone that is that has a helium cavity in it, and so that's a use to save on power. So you, of course, the drone is complete lift, so you want to keep the weight down, and that's always a factor in airplane design, using materials like composites. I remember once I went to a factory where they were building, I think it was back in the F-14 or F-16 days, but they had a machine shop, and they took a complete single block of aluminum and carved it out, and that was the frame for the F-14 fighter. I think it was the F-14. And then they would add all the parts onto that, but it was a single block of aluminum. Tremendous amount of machining. And then along came Burt Rutan and the composite revolution for aviation. Okay, here's a blimp that is a modern version for transporting people, and you see the I don't know if they're electric, they appear to be electric propellers, ducted fans on the side, but once again a blimp. And here's a prototype of the Zeppelin. Now the Zeppelin was built with an aluminum frame. These were like the Hindenburg is the most famous Zeppelin. It was almost as big as the Titanic ship, just to give you an idea of size, 804 feet long, tremendously huge spacecraft or aircraft. And they were going regularly between Germany and New York, and Germany and Brazil, and I think Germany and Argentina, post-World War II. But it would take a couple days. That was something that was very interesting, because they don't go very fast. and their top speed is, I don't know exactly the top speed, but relatively slow. But over moving constantly for over the period of 2 days, they could get from Germany to New York. And I'll show some pictures of the Hindenburg coming in. Here's a picture of the aerodynamic forces on an airfoil. You have the flow coming in, which the wing has to overcome. Then you have the lift and the drag, and so also there's the weight of the aircraft that pulls down. And so what you want to do is reduce the weight of the aircraft and make the aerodynamic lift commensurate with the size of the airplane. And the aerodynamic lift is something that's truly amazing. Look at a big jet like a 777 or a 747. And those wings, relative to the amount of weight it has to lift, are not very big. It's truly amazing. Okay, here's a picture. This is actually a picture of the Hindenburg, and you can see if you look closely, the little people out there, this is the actual Zeppelin Hindenburg. And you can see it's being moored at this base. Here are a number of designs of, probably in the 1800s, where people were designing these. Even you go back to the Middle Ages, people were, Michelangelo and people like that were designing rotors and propeller systems, etc. Okay, here's the one I was telling you about. Here's the one that has like little fish fins that move it along. There's a little crank system there that makes the fins move. Here's the Graf Zeppelin, and so is one of the designs. Now you can see the ribbing here, and so what they did, there's a couple pictures coming up showing the fabrication, but first of all they make this frame and then they stretch the skin over it. And I think one of the problems with the original skin of the Hindenburg was that it had a high aluminum content. Okay, so let me move through these a little faster. Here is the Hindenburg coming in over Manhattan. Okay, this is interesting. This is the Hindenburg brochure, 1937, 2 days to Europe. And I think they could carry about 150 people with absolute extensive luxury. That's what they said. The best wines, the best aged liquors, the best food. They had cooks on board, and of course the people slept there 2 days. They said it was like the finest hotel possible and rivaled the Titanic for luxury. But anyway, that was a brochure from that era showing the layout of the staterooms, etc. Here's a modern version of a blimp, and people are building these. Now there's some back and forth as to the usefulness. Some people are trying to build replicas of the big blimps and then use them for cargo. But the problem is, even though you can get out into remote locations, etc., the problem is, okay, you have this big heavy load and you come down, you drop off the load. All of a sudden, you've got this blimp full of air that has tremendous amount of lift, and it just goes up. Very hard to control keeping it on the ground. So you can load something else in it and move it again. So it's kind of a contradiction because they have so much lift capability, but then when you drop off that cargo, now you need some kind of weight to keep this thing stable. Here is the picture of what is known as the Honda Jet. This is the short version. There's a longer version that they say can fly from New York City to Los Angeles on a single fuel. But this is the reason I'm showing this is because imagine this aircraft, but a little bit fatter, a little bit shorter wings, much less power. You don't need those two jet engines, and inflatable. And so this Honda Jet, I believe, is around $1 million, $1.5 million. They say it's affordable by the average person. Well, not by anybody I know, but I'm not on the level of knowing people that have their own private jets. But the idea is that this will, for a family of 6, this will take you and your family and all their stuff to wherever you want to go. The problem is you need an airport. You need an airport to house it, you need an airport to land, and then you need transportation when you get there. So, but for people with a lot of money, that's not a big deal. But it's said that you can drive this yourself. But imagine this, like I say, imagine this a little bit expanded with the body of the aircraft, a little bit shorter wings, and I'll show you a design at the end. But the idea being that you have an inflatable, helium inflatable aircraft, and the lift is not really necessary because you have the helium in there. And if you have, if say you're going 100 miles an hour instead of 400 miles an hour in a jet, you're going 100 miles an hour, but it's very comfortable. That is the ticket. Okay, so we'll come back to this. This is the inside of a Honda Jet. Pretty nice if you can afford it. A hot air balloon, one of the oldest ways of getting around, but of course very little control. You're completely subject to the wind, and that's the other thing, is what do you do in inclement weather? What do you do with the hot air balloon? You can only go in the direction of the wind. Okay, so here's an interesting design where the wings actually flop like a bird's wings, and that's like a design, somebody's design. Here's the Goodyear blimp I was talking about, used extensively for sporting good events. Flying Whales, this is a modern company that is promoting this dirigible as a, and here's another one. Here's Lockheed Martin, and they're for military use, obviously. You can see that this is an artist's conception. It's hybrid airship, they call it. Here's a solar ship that I don't know all of the details of all of these, but this has little propellers on it to make it move. This is I forget, I can't see the name on the tail there, but once again, this is a design for utility. Here's in Lockheed Martin, and they have these ducted fans pointing down, and I think the idea is that they can be pointed up or down. An Airlander, another blimp. Here's one, the Skyhook, and this is what I was talking about. If you drop off a heavy load, off in a remote place, or for emergency, etc., then what do? Now you have much less ballast in your spacecraft or your aircraft. Here's the Hindenburg being built. Like I said, it's a big aluminum frame with skin on top of it. Here's another view. And this is a aerodynamic chart for helium. Helium, 1 cubic foot can lift 1.1 kilograms. Hydrogen, about 1.2 kilograms. And then hot air, about 0.35 kilograms per cubic foot. No, I'm sorry, per cubic meter. That's a lot of space. Okay, now here is something along the lines. This is a little model, once again, with a turbine on the bottom, and a craft that is partially inflated with helium. Okay, now I want to also show the following. Now I saw an aircraft that was designed like this, and I couldn't find it, so I made some drawings, and so I'll just end with that. But this is the wave of the future, I believe, and we'll be seeing more of these. But I think it would be kind of fun to be able to go out and go camping. Just go out in the middle of nowhere, nobody around. Go find a secluded area on the side of a lake someplace. You could even land on the water. And that's the thing, is you don't need an airport to take off or land. So with that fun thought, I'll leave you, and we'll talk to you next week.
This has been Master of Science with host James McCanney. Join us each week as James will delve into historical figures such as Nikola Tesla, Albert Einstein, and the great mathematicians as we explore the history of man, Earth, and our universe as you've never seen it before. Tuesdays, 7 p.m. Eastern, right here on the Bold Brave TV network, powered by B2 Studios.